Section 24. Cosmological History of Our Universe. Cosmologists have this history of our universe in 15 seconds. First there was nothing. Then there was something. Then there was hydrogen. Then there was dirty hydrogen. First the dirty hydrogen was ionized. Then it was neutral. Then it was ionized again. Here is a beautiful and useful visualization of the history of the universe. Time increases left to right. At specific times, a circular hoop is drawn. The radius of the hoop is a loose representation of the scale factor at that time, so of the expansion of the universe. This helps us to see different epochs and how the distance between distant galaxies has increased over time. But it is not a timeline of individual galaxies. So here we see primordial fluctuations, cosmic inflation, atoms forming, cosmic microwave background would be here. First stars forming, first galaxies forming, and so forth. Now the detailed version of the history of our universe. This graph shows the scale factor for the entire history of our universe plus 120 billion years into our probable Big Chill future. The horizontal scale is the logarithm of time in seconds since the Big Bang, from -50 on the left to +20 on the right. The vertical scale is the logarithm of the scale factor, from -60 at the bottom to +10 at the top. Let's recap some of our universe's past. There will be some new information about particles for the first second. For times after 1 second, this will be a limited repetition of material we have already covered. For more information, go to the main course. We will use the phrase Big Bang for the start of our universe before the Planck time, not the period through cosmic microwave background last scattering. We will start with the Big Bang and move forward in time. So lower left to upper right. At the Planck time, the universe was extremely hot and dense. 10 to the 32 Kelvin temperature, 10 to the 16 tera-electron volts radiation energy. Before and at the Planck time, quantum mechanical effects and quantum field theories were as important as gravity, and general relativity must be replaced with a verified theory of quantum gravity. But we don't have one, so physicists do not know what happened in that regime. See also the theory of everything on Wikipedia. The time before the Planck time is called the Planck epoch or Planck era, and there are no testable theories for this regime. Though the radiation particle energy density and average energy were immense at the Planck time, there was only one radiation particle within the cosmic particle horizon volume at the Planck time. The universe cannot be considered smooth at that time, and general relativity does not apply. Supplemental video number 7 discusses Planck units. After the Planck time, so here, gravity became weaker than the other fundamental forces, and general relativity applies. We can use the Friedmann equation, assuming its assumptions were valid. It is assumed that there were quantum mechanical energy density and temperature variations throughout the universe that began with the Big Bang or the Planck time. After the Planck time, the strengths of all fundamental forces, interactions, except gravity, were equal. Gravity was weaker. Our electromagnetic force and weak interaction were different in the early universe, combined into the electroweak, hypercharge, and isospin forces. Elementary particles then were massless and traveled at the speed of light, but they had different characteristics than a trillionth of a second later or now. Physicists do not know for certain because this energy regime is more than 1 trillion times higher than the Large Hadron Collider. Expansion is presumed dominated by radiation, but the particles were different than photons at this early time. Prior to 10 to the minus 36 seconds, the electroweak forces and the strong nuclear force are believed to have been unified, and elementary particles were different in that grand unified epoch. See also Grand Unified Theory on Wikipedia. Around 10 to the minus 36 seconds, the temperature fell to 10 to the 28th Kelvin, and the strength of the electroweak forces fell below the strength of the strong nuclear force. They were no longer unified. Perhaps there were quarks, gluons, and color charge after this time, but the quarks were massless for the time being. Sometime before 10 to the minus 32 seconds, there is assumed to have been an exponential expansion called cosmic inflation. The universe is thought to have expanded by at least 26 orders of magnitude in 10 to the minus 33 seconds, much faster than the speed of light. Any initial curvature of the universe became reduced to nearly zero after inflation. This is the end of inflation. Early quantum mechanical variations in energy density and temperature were greatly reduced after inflation, such that our cosmic microwave background is uniform to 10 parts per million. Our current observable universe was about 5.6 meters in diameter after cosmic inflation. 10 to the minus 33 seconds after the Big Bang or Planck time. All points in our present observable universe were in causal contact and thermal equilibrium prior to inflation, here. There may have been magnetic monopoles in the universe before inflation, here, but their number density was diluted by the cosmic inflation, and it is assumed that there are none within our present observable universe. Radiation temperature fell drastically during inflation, but was then reheated to its temperature prior to inflation. I have not read anything about temperature and particle physics during the inflation period. Once reheating completes, the temperature is inversely proportional to the scale factor for the remainder of the history of the universe. Some authors use the end of reheating after cosmic inflation as their Big Bang time, rather than the time before cosmic inflation or before the Planck time. And some other authors use recombination and last scattering as their Big Bang time. At the end of inflation, the strength of the electroweak forces was 1/100th of the strength of the strong nuclear force. All elementary particles, including quarks, had zero rest mass at this time, but quarks and gluons did have color charge, so perhaps quarks had some effective mass due to their clouds of gluons. I don't know. After inflation, and for the next 50,000 years, the expansion of the universe was dominated by radiation. Elementary particles moving through the universe at or near the speed of light. Radiation energy density was proportional to 1/4 power of the scale factor. The scale factor was increasing proportional to the square root of time, increasing but decelerating. Radiation energy density was decreasing proportional to 1/the square of time. The radiation temperature was decreasing proportional to 1/the square root of time. At the end of this section, I give a chart of temperature versus time. After inflation, radiation temperature falls as the universe expands, as does the energy density and pressure of radiation, and later, matter. At 10 to the minus 12th seconds, the temperature and radiation particle energy fell to about 10 to the 16 Kelvin and 3 tera-electron volts. This is within the energy range of the Large Hadron Collider, so particle physics is pretty well understood and verified as of that time. The radiation particle energy is falling below the mass of the Higgs boson. The Higgs field turns on, breaks electroweak symmetry, and gives other elementary particles their mass and their electrical charge. The color charge of quarks and gluons probably existed before this time. The prior electroweak hypercharge and isospin forces became replaced with our present electromagnetic force and weak interaction. The weak interaction became much weaker than the electromagnetic force and extremely short-ranged versus the infinite range of electromagnetism. After that time, ordinary matter elementary particles and forces had the same properties and values as they do today. Now, there were photons, neutrinos, electrons, and quarks as we know them today. Ordinary matter, not cold dark matter, consisted primarily of relativistic quark-gluon plasma, whose density everywhere in the universe was higher than a proton's density today, much denser than a nucleus or a neutron star. There were also muons, antimuons, electrons, and positrons. At 10 to the minus 6 seconds, the temperature and photon energy fell to about 10 to the 13 Kelvin and 3 giga-electron volts. If dark matter consists of elementary particles, and if they were created by neutrinos or via the weak interaction, this probably occurred in the first microsecond, but physicists presently have no information. At about 10 to the minus 4 seconds, the temperature and photon energy fell to 1.3 by 10 to the 12th Kelvin and 300 million electron volts. Quark-antiquark pairs stopped being produced. The liquid-like quark-gluon plasma was much less dense than a proton, and it evaporated to produce distinct baryon particles, such as protons. Though quarks and antiquarks were believed to have been created initially in equal numbers, comparable to the number of photons, and should have annihilated in equal numbers, leaving 0 baryons in the universe, somehow there was a small residue of protons and neutrons. Somehow 1 out of a billion antiquarks or antiprotons and antineutrons decayed to leptons, violating conservation of baryon number, but keeping the universe electrically charged neutral. This is called baryogenesis. Physicists know the 3 conditions required to cause this, some of which have been observed in experiments, but they do not know the specific mechanism and process at work in the first second of the universe. From 10 to the minus 4 seconds to 1 second, or 1 second to 10 seconds, is sometimes called the lepton era or lepton epoch, as the dominant matter particles were relativistic muons, electrons, and neutrinos after most quarks and baryons annihilated and were no longer produced. Then muon-antimuon pairs ceased to be produced and annihilated. Before 1 second, neutrino-antineutrino pairs ceased to be produced, but could no longer annihilate because their energy fell below the electron rest mass. Neutrinos had decoupled, freeze out, from other matter, electrons and positrons. These cosmic neutrinos and antineutrinos have been traveling the expanding universe since the first second, losing energy due to cosmological redshift. Neutrino rest mass energy is small, much smaller than an electron, so neutrinos were relativistic and count as radiation for most of the age of the universe. Physicists might be able to directly detect these cosmic neutrinos on Earth in the next decade. Two seconds after the Big Bang, the energy density of radiation, photons and neutrinos, was 1,000,000 times the energy density of matter, and 82,000 times at 5 minutes. So radiation dominated expansion of the universe. There were protons and neutrons, but all antiprotons and antineutrons were gone by then. At 2 seconds, the temperature was hotter than the core of the Sun today, but the density of protons and neutrons was less than the density of water today. From 2 seconds to 5 minutes, all neutrons became bound with protons, first as deuterium nuclei and then as helium-4 nuclei, with only a small amount of deuterium, helium-3, and lithium. This is called Big Bang nucleosynthesis. No carbon, oxygen, or nuclei heavier than beryllium were produced. We covered this in more detail in the main course. At the end of Big Bang nucleosynthesis, the ordinary matter mass fraction of hydrogen-1 single protons is 76%, and the mass fraction of helium-4 is 24%. This will be the starting composition of the first stars when they form later. The mass fractions are an important source of information for confirming the hot Big Bang and understanding the parameters of our universe. In this period, electron-positron pairs ceased to be produced and annihilated. Though electrons and positrons were believed to have been created initially in equal numbers and should have annihilated in equal numbers, leaving 0 electrons in the universe, somehow there was a small residue of electrons exactly balancing the charge of the residue of protons. This is called leptogenesis. The temperature is still hot, so the nuclei and electrons are in ionized plasma state, not neutral atoms. Cold dark matter was 85% of total matter, as it is today. The cosmological properties of dark matter are inferred. It has not been detected directly. The adjective cold means non-relativistic when the universe was tens of years old, such that it did not count as radiation. Dark means rarely, if ever, interacting with light or with ordinary matter. Scientists do not know what dark matter consists of, when it was created, or if it has ever interacted with light, ordinary matter, or itself, other than through gravity. Radiation energy density was proportional to 1 over the 4th power of the scale factor, and non-relativistic matter energy density was proportional to 1 over the 3rd power of the scale factor, a faster decline for radiation than for matter as the universe expanded. At 50,000 years, the temperature was 9,400 Kelvin. The energy density of radiation falls below the energy density of matter. An expansion of the universe is then dominated by non-relativistic matter. The scale factor was now increasing, roughly proportional to the 2/3 power of time, increasing but decelerating. Matter energy density was decreasing, proportional to 1 over the square of time. The radiation temperature was decreasing, proportional to 1 over the 2/3 power of time. From 220,000 years to 370,000 years, the radiation temperature had cooled from 4,000 Kelvin to 3,000 Kelvin. Over this period, protons and electrons combine to form neutral hydrogen atoms. This is called recombination, even though they had never previously been combined. Neutral helium atoms had already formed. the universe was no longer a plasma scattering the photons, and so then photons could stream freely through the electrically neutral, expanding universe. We see these final last scattering photons today as the cosmic microwave background, having been redshifted by a factor of 1090 since they were emitted at that time. CMB measurements are an important source of information for confirming the hot Big Bang and understanding the parameters of our universe. Our current visible universe was about 25 megaparsecs in diameter when this light was emitted at CMB last scattering. That last scattering light quickly redshifted from visible to infrared, and there were no stars yet, so this is called the beginning of the Dark Ages. While ordinary matter was still an ionized plasma, so back here, slight overdensities of dark matter began to contract and pulled ordinary matter along to contract. These would have later formed stars and then galaxies. The first stars were massive, fused hydrogen rapidly, and began to shine sometime around 50 to 400 million years. The star's ultraviolet light reionized the hydrogen atoms to protons and electrons, first near the stars, then in the galaxy, then near the galaxy, and ultimately the entire universe, including the cosmic voids. This is the epoch of reionization. However, the plasma density was now low, so mostly transparent to CMB photons. Nearly every galaxy is believed to have, at its core, a rotating supermassive black hole of mass several hundred thousand to billions of solar masses. Cosmologists do not know when those black holes initially formed. Gas and shredded stars spiraling toward the black hole event horizon, an accretion disk, heats up and high-energy particles escape in two jets in opposite directions. Early in the life of a galaxy, the jets can be brighter than the stellar core of the galaxy. These cases are called quasars or active galactic nuclei, AGNs. Over time, the immediate area of the black hole gets cleared out. More information is available in the course on gravitation and black holes. Dark energy presently appears to be a small, constant or nearly constant energy density of the space of the universe. Not a constant amount of energy in the expanding universe, but a constant energy density. Perhaps it is a property of our universe. Perhaps it is the energy density of the vacuum of space. Perhaps present cosmological assumptions and theories are wrong. If dark energy density has been constant over time, then at 7.6 billion years, 6.1 billion years ago, which is like here, the energy density of matter fell to twice the dark energy density. Prior to this time, the scale factor was increasing but decelerating. After this time, the scale factor is increasing and accelerating. This is the accelerating expansion of the universe due to dark energy. At that time, the scale factor was 0.61, redshift Z was 0.64, and the radiation temperature was 4.5 Kelvin. At 10.2 billion years, 3.6 billion years ago, the energy density of matter fell below the constant energy density of dark energy. At that time, the scale factor was 0.77, redshift Z was 0.3, and radiation temperature was 3.6 Kelvin. Dark energy has dominated the accelerated expansion of the universe since that time. Expansion has accelerated and is expected to become exponential in the future, increasing by a factor of 10 every 40 billion years if dark energy density is constant, independent of time and scale factor. Cosmologists refer to this case as W equals -1. Presently, it looks like our universe will continue to expand forever. The distance between distant galaxies will continue to increase, but the galaxies themselves will remain intact galaxies, and galaxy clusters will remain galaxy clusters. The distance between galaxy clusters will continue to increase. This future is called the Big Chill. Stars in our galaxy will continue to age. The Andromeda Galaxy will merge with the Milky Way. But galaxies beyond our local group will appear dimmer and redshift into the infrared in future. There will be no end of time, but the cosmic microwave background temperature will get colder and colder over time. If dark energy density decreases with scale factor, but W is more negative than -1/3 and less negative than -1, our universe will still end with a big chill, but the time evolution will be slower. If dark energy density increases with scale factor, W more negative than -1, the increasing energy density of dark energy will eventually rip galaxies apart, then rip stars apart, then rip all matter apart. This possibility is called the Big Rip. If this were to happen, a time would come when the universe ends with infinite scale factor, likely more than 100 billion years from today. The time of the universe's end is a sensitive function of W. Cosmologists want to better determine if dark energy density is constant or evolves, and how it evolves as a function of scale factor and/or time. A universe can contract and end in a big crunch or in a big bounce, but presently this appears not to be the future of our universe. For reference, here is a graph of radiation temperature versus time.